a very warm good morning to everyone. And thank you for joining us for this one-week faculty development program titled GIS and Remote Sensing, organized by Department of Civil Engineering, Government Engineering College Bilaspur, and sponsored by AICTE under the AICTE Technical and Learning Academy, that is ATAL scheme. I, DP Singh, Assistant Professor at GIS Bilaspur, and your host for the session, feel privileged to extend my warm welcome to one and all presented here. So to begin with this introductory session, I would like to invite Dr. Seema Chauhan, Associate Professor, Department of Civil Engineering, and also the coordinator of this workshop to give a brief detail regarding this 5 days faculty development program. Seema ma'am.
Yes, thank you, Deepti. Respected Dr. B.H. Chawla, Principal Government Engineering College, Bilaspur. Respected Ashish Joshi, Scientist from Indian Institute of Remote Sensing, Dehradun, Speaker of our first session. Dr. S.K. Singhai, Professor and Head of the Department, Electrical Engineering, Government Engineering College, Bilaspur. Dear participants, Head of the Departments of GEC Bilaspur and faculty. A very good morning to all of you. On behalf of the Government Engineering College, Bilaspur, I welcome you all for this 5 days online ATAL Faculty Development Program on GIS and Remote Sensing, starting from today, organized by Civil Engineering Department of Government Engineering College, Bilaspur. The objective of this workshop is to train the faculty members, research scholars, young scientists, and postgraduate students of various organizations in the field of GIS and remote sensing. The objective of the program is also to provide a platform of interaction, exchange of ideas of recent trends, and future advancement in the field of GIS and remote sensing with the experts from Indian Institute of Remote Sensing, Dehradun, ISRO, IIT Kharagpur, NIT Raipur, State Technical University, Bhilai, and State Agriculture University, Raipur. We are happy to inform that for this FDP, we have received very good response. 171 participants from 19 states of India have registered for this FDP. We would like to thank all the participants for registering in this program. We have participants from different disciplines of engineering and other fields like architecture, physics, chemistry, economics, geography, data science, remote sensing. In all, we have a wide, diverse audience over here. We are thankful to AICTE Training and Learning Academy for accepting our proposal for FDP and funding this FDP. We have planned to cover the basics of GIS and remote sensing and its application in these 5 days FDP program. Overall, 14 sessions are planned, in which 6 sessions are devoted for basics, 6 sessions for application, and 1 session for GIS open software. And as per AICTE guidelines, 1 session is kept for stress management. A test will be conducted at the end of the program. Each day, there will be 3 technical sessions. Its schedule has already been shared to all the participants. Session-wise attendance of the participants will be managed by us. Dear participants, as per AICTE directives, only approved candidate will get the certificate. ATAL Academy will issue the certificate to those participants who have attended the program with minimum 80% attendance and scored minimum 60% marks in the test. We hope we will have an exciting learning experience with our experts, and we also hope that this FDP is going to be useful both for the beginners and advanced learners in this area. Once again, I welcome you all. Thank you.
Thank you so much, ma'am, for a very informative introduction. Moving ahead, I now request Dr. S.K. Singhai, a Senior Professor and Head of the Department Electrical Engineering, to share his view with us.
Thank you, Deepi. Good morning, everybody. Can you hear me?
Yes, sir.
Okay, thank you. Respected Principal Dr. B.S. Chawla sir, all experts for this FDP, Course Coordinator Dr. Seema Chauhan, Assistant Course Coordinator Ms. Preeti Rajput, and my dear participants from all parts of the country. I am Dr. S.K. Singhai, Professor and Head of the Electrical Engineering Department at this prestigious institute of the state Chhattisgarh. I welcome you all on the behalf of my institute and organizing team of this FDP. Being an accredited department, that is Civil Engineering Department, we at Government Engineering College Bilaspur follow outcome-based education. And so, this course has also been designed to meet certain outcomes. We have chosen the experts also accordingly, and our coordinator has very carefully designed the whole syllabus for this course. So you will see throughout this course that if you miss certain lectures, then you will find it difficult to understand the next lecture. So I expect all of you to please attend all the lectures regularly. We expect that at the end of this course, you will have certain tangible outcomes in your hand, and you will be able to do something by your own. We are also very particular about the discipline, and so we want that everybody starts attending the session in time, give tests seriously, and finally give the feedback on AICTE FDP portal so that you are enabled to get a certificate. Some people think that online education is not for serious studies, but we will try to break this myth through this course. This mode of learning will certainly catch up even after pandemic because it is very convenient, cheap, eco-friendly, accessible, and very interesting also. Lot of experimentation is already going on for this online education, so that you will see in this course. So please be attentive. Feel free for any technical support from our end. And finally, I wish you all a great learning experience. Thank you very much. Thank you.
Thank you so much, sir. Moving ahead, we are limited not by our abilities, but by our visions. And leadership is a capability to translate vision into reality. With these words, I would like to invite Dr. B.S. Chawla, Principal Government Engineering College Bilaspur and patron of this FDP to share a few words with us.
Thank you,
Sir.
Deepi. Thank you, Deepi. Very good morning and warm welcome to all the participants here to this 5 days FDP sponsored by ATAL on GIS and Remote Sensing. Sri Ashish Joshi ji, expert speaker for today's inaugural session from Indian Institute of Remote Sensing, Professor Singhai, Professor M.L. Agrawal, Professor G.K. Agrawal, other HODs, Dr. Seema Chauhan Madam, coordinator of this program, and her team, all faculties from this college, supporting team members, Professor Vivek, Professor DP, all participants attending this program from various different corners of the country, from various organizations. I would like to tell you in brief about the host institute because many of you may not be knowing about us. This college was established by government of Madhya Pradesh that time in 1964. We have celebrated our golden jubilee 5 years back. We offer 7 UG programs with intake of 273, and this year we have started our first PG program in thermal engineering. We are having 4 research centers, PhD research centers in 4 different branches, which are contributing, which will be contributing significantly in coming days. Out of 7 courses, 4 courses are NBA accredited. With this honor, we are the only institute in Chhattisgarh from government side. We were recipient of this TechUp 2 and TechUp 3 projects too. Very successfully, we concluded TechUp 2 and TechUp 3 is also going to conclude soon. In this college, around 70 well-equipped labs and a very rich library we are having, which is having this ebook facility too. For the staff who are working in this college, they have residential facility. With 5 hostels, we are able to accommodate almost 50% of the intake who are here for studies. Our college is having track record of 100% admission every year, and being located in Bilaspur, almost 60% of the rural area students are able to get education from this college. All the government policies are strictly implemented here, whether they are related to scholarships, reservations, or employment. The recruitment in this college is through national open competition, that is Public Service Commission. Very recently, last month, successfully, we organized one ATAL FDP on infrastructure engineering under dynamic leadership of Professor M.L. Agrawal, HOD of Civil. And this is our second FDP in the series. We are expecting many more in coming days. As you all are aware, GIS and remote sensing is very demanding topic. And for any effective planning, we need data. These data get compiled through GIS and remote sensing, and we'll see in the planning of smart cities or property mapping for taxation purpose or e-governance or civic planning, whether it is health, medical resource management, disaster management, effective transportation, etc. These will be the areas which will be having effective policies formulation only because of GIS and remote sensing. I'm sure the experts which we had chosen from the Indian Institute of Remote Sensing, the various senior scientists, faculty from IIT Kharagpur, from NIT Raipur, are very distinguished alumni who led this Chandrayaan project from ISRO, Deputy Director, Mr. Alok Srivastav, then faculty from Technical University and Indira Gandhi Agriculture University. They will be able to give you accurate input, and they will definitely enhance your knowledge in these 5 days. I'm thankful to all these resource institutes who have provided us experts and extended all cooperation, in particular to AICTE, our alumni, Mr. Chandrasekhar Verma, who is RO at Bhopal, Government of India World Bank Project under TECO, Government of Chhattisgarh, Department of Technical Education. I'm thankful to all. I wish you all very fine and very nice days in coming time. And these 5 days will be definitely memorable for you. In this pandemic scene, this new normal, you all will be able to get benefit from this. And online course will be very much effective. This I'm sure. And in case of any problem, you all are welcome. You can share your feedbacks. We'll try to give you the best. Thank you again. Wish you good luck. Thank you.
Thank you so much, sir. A little housekeeping before we get started. AICTE is organizing a common inaugural ceremony for all 46 courses from 11 a.m. A link related to this ceremony will be shared in the WhatsApp group. All of you are requested to join this inaugural ceremony. Moreover, we have assigned last 10 minutes of the session for question answer where you can ask your doubts related to the presentation. So without much ado, let's start the very first session of this FDP titled Basic Principle of Remote Sensing, Earth Observation Sensors and Platforms, presented by Mr. Ashish Joshi, Scientist Engineer at Photogrammetry and Remote Sensing Department at Indian Institute of Remote Sensing, Dehradun. He has joined ISRO in the year 2010 and having more than 10 years of working experience in the field of optical and SAR satellite data processing. Moreover, he has worked on various Indian remote sensing satellite projects and expertise in radiometric and geometric direction algorithm, Infra-red and DEM. Parallelly, he has also worked on different satellite orbit and attitude transformations, interpolation and simulation. Sir, I extend a warm welcome to you and request you to start the session. Ashish sir.
Thank you for giving me the opportunity.
Hello. Hello.
Good morning to all. Myself Ashish Joshi. I am working as a scientist at Indian Institute of Remote Sensing, Dehradun. Today I will take the lecture on the basic principles of remote sensing, Earth observation sensor and platform. So, what is remote sensing? The science and the art of obtaining information about an object.
मोबाइल से कनेक्ट कर रहे हैं। अच्छा, तो मोबाइल में वो लॉगिन है ना आपका, मतलब ये MS टीम का वो? अच्छा, एज अ गेस्ट। अच्छा, ठीक है, एक बार ट्राई करके देखिए सर।
The science and the art of obtaining the information about an object, area or phenomena through the analysis of data acquired by a device that is not in contact with the object, area or phenomena under investigation. So the remote sensing is the art of obtaining the information of any object without being in contact. So in our daily life, we are doing the remote sensing with our eyes. So the eyes are the remote sensor. So we are getting the information of the objects with the visible light spectrum, and we are observing the objects, and our brain is doing the analysis and the data processing part. So the remote sensing is the science of obtaining the information of any object without being in contact with the physical object. Now there are three things in the remote sensing. First is the sensor, second is the electromagnetic radiation, and third is the object. So through the sensor, the information about the object is obtained. In remote sensing, the sensors are not in the direct contact with the objects of events being observed. The electromagnetic radiations are the information carriers. They are normally used as an information carriers in the remote sensing. And the object is the object what we want to study. So basically there are three things. One is the sensor, one the object to be sensed, and how to get the information of the object. We are using the electromagnetic radiations. So there are different components of the remote sensing. First is the energy source. So the energy source will emit the radiation. These radiations are interacted by the targets. So the radiations either absorbed, transmitted or reflected towards the sensor. So the reflected energy is recorded by the sensor. So this recorded energy is converted from analog to the digital form, and then it transfers from the sensor to the ground receiving station. And these ground receiving centers will process the data, and the processed data is given for the analysis, and then these products are given for the application. So there are basically different components in the remote sensing which for doing the analysis of any object. So there is basically two types of remote sensing. One is passive and another is active remote sensing. So most of the remote sensing systems are passive. They use the energy provided by the sun and earth. So here we can see in this figure, the sun provides the energy and the passive energy is sensed by the sensor. So this is called the passive sensors or passive remote sensing. In the active remote sensing, the sensor generate their own energy. like radar, they emit the electromagnetic radiation, and these backscattered electromagnetic radiations is again observed by the sensor. So in the active remote sensing, they are the self illumination is there in the active remote sensing. So the example is the SAR and the LIDAR. In the SAR is the synthetic aperture radar, and LIDAR is the light detection and ranging. So it works in the SAR works in the microwave region, and the LIDAR works in the visible region. So these are used for the imaging and the altimetry. So what we can see, like passive uses the sun energy. It has no own source of illumination, but the active sensor has the own source of illumination. They emit the electromagnetic radiations, and then the backscattered energy is analyzed by the sensor. So the passive sensor, the sun energy is either reflected in the visible or infrared wavelengths, or absorbed and then re-emitted in the thermal infrared wavelengths. For all reflected energy, this can only take place during the time when the sun is illuminating the earth. So in the passive sensor, if we are using the visible part, means reflected in IR part, then it can only be used during the daytime. And in the night time, we cannot do the remote sensing for the passive sensor, which are using the visible and infrared wavelengths. But the energy that is naturally emitted, such as thermal infrared, can be detected day or night. So, thermal remote sensing, we can image the as Earth's surface at the night time also, because the radiation which are emitted are being observed during the thermal remote sensing. So in the optical remote sensing, we are doing the at the daytime, but in the thermal remote sensing, we are doing as well as day and night. So these are the passive sensors. Now, SAR or radar is an active sensor which provide their own energy source for illumination. So these sensors emit the radiation which is directed towards the target to get the information. The radiation is scattered from the target is detected and measured by the sensor. The advantage for active sensor include the ability to obtain the measurements anytime regardless of the time of day or season. So here the SAR or LIDAR will illuminate the electromagnetic radiation, and the backscattered radiations are being observed by the sensor. So active sensor can work both day and night because they have own source of illumination, and they basically works in the microwave region or visible region. So synthetic aperture radar works on the microwave region, and the LIDAR works on the visible region. So this is the pictorial representation of the passive and the active remote sensing. Here the sun is the source of illumination. So this energy is sensed by the passive sensor. So in the optical or IR remote sensing, this reflected sunlight is being observed by the passive sensor. And in the thermal remote sensing, the emitted energy is sensed by the passive sensor. And in the active sensor, it will also emit the electromagnetic radiation, and then backscattered radiation is observed by the active sensor. So what does a sensor measure? So basically it measures the three components. One is the reflected energy, other is the scattered energy, and third is the emitted energy. Means reflected energy means when the radiation interacts with the target, then it reflected in the opposite direction using the Snell's law. So that energy is observed by the passive sensor. The scattered energy means the scattering through the surfaces or the atmosphere is being observed by the sensor. And the emitted energy means after the reflection, the reflections are absorbed by the surface and then again emitted. That emitted radiations are also sensed by the sensor. So first we will go through the interaction with the target, how the electromagnetic radiations interacts with the target. So basically there are three forms of interaction. One is the absorption, second is the transmission, third is the reflection. So what is the absorption? Radiation is absorbed into the target. Transmission means radiation passes through the target. And the reflection means radiation bounces off the target and is redirected. Okay. So there are three components: absorption, transmission, and reflection. So if we see the leaf, if any electromagnetic radiation falls, so this is the incident energy. So either it will reflect, or it can be
हाँ
absorbed
तो
by
अभी
the
तो लेटरल एडमिशन हो ही
leaves,
रहा है यार
or it
मतलब
can be
मेरे को
transmitted
उसका
through the
नोटिस अभी याद
leaves.
नहीं है लेकिन
Okay, so
हाँ अभी कुछ
these three
दिन पहले आया
phenomena
तो
will
था
occur
कुछ
with the
इससे
interaction of the
होगा
target.
वैसे ये मेरे ख्याल
So
से 12 तक था क्या या
when the solar
डेट
energy is
एक बार कंफर्म करना
surface,
पड़ेगा
the energy either observed, transmitted, or
डायरेक्टरेट ऑफ
reflected
टेक्निकल
in
एजुकेशन के
accordance with the
वेबसाइट पे भी
law
जा
of the
सकता हूँ कभी
conservation
भी
of
मिल जाएगा
energy.
मेरे को
So the
तो मैं
incidence
खोजता हूँ
energy is
हमारे
the sum
फैकल्टी
of
ग्रुप
the
में शेयर तो हुआ
absorbed,
था
transmitted,
और मेरे को जहाँ तक
and
याद आ रहा है 12
reflected
में
energy.
उसका वो था
But in the remote sensing,
एडमिशन
we are
चल रहा था
most
आज का
interested
मेरे को
in
पता नहीं
measuring
आएगा
the radiation reflected from the target. So basically in the optical remote sensing, what we will do, we
हाँ
will
बात
see
करो
the
लेकिन किस रिगार्डिंग है
reflected part of the
एडमिशन
electromagnetic
के रिगार्डिंग आप
radiations
काम कर
in
स्टूडेंट
the
सेक्शन से बात कर रहे थे तो मेरे
optical
को
remote
जानकारी है
sensing.
नहीं तो मैं भी क्या बताऊंगा वहाँ पे श्रोते जी हैं
So the portion
श्रोते
of
जी
the
से बात
energy
कराएगा ना तो
reflected,
वो
absorbed, and
पूरा बता
transmitted
दें
will vary depend on the surface material. Means different surfaces are there,
है ना
then they will reflect, absorb,
वो
and transmit it
करता हूँ
according to
क्योंकि
the
मैं बात
material
करता हूँ क्योंकि वो
of the
स्टूडेंट सेक्शन
earth's surface.
वो
So
बताएंगे
vegetation and the soils can reflect approximately 30 to 50% of the incidence energy. So they have the high reflection. Now, but the water, on the other hand, reflects only 10% on the incidence energy. It reflects most of this energy in the visible range and minimal in the NIR, and beyond 1.2 mm mid-infrared, all energy is absorbed. Means different features of the earth reflects differently. Means vegetation and soils reflect 30 to 50%, and water reflects 10% of the incidence energy. So our optical sensors measure this energy. So if any target which reflect more energy, we will see as a bright object. Means we will see the in the image higher value for the higher reflectance object and lower value for lower reflectance. So water will appear as a black or lower value, and the vegetation appears as bright in the images of the satellites. Now, second is the interaction with the atmosphere. So I have told about the interaction with the target. Now I will told about the interaction with the atmosphere. So basically, in the interaction with the atmosphere, the scattering will occur. Now, what is scattering? Scattering occurs when particles or large gas molecules present in the atmosphere interacts with and cause the electromagnetic radiation to be redirected from its original path. So scattering differs from the reflection in that direction associated with the scattering is unpredictable, whereas the direction of reflection is predictable. Means whenever any electromagnetic radiations will strike the gas or molecules, then it will again rebounces in different direction in the scattering. But in the reflection, it follow the Snell's law. It will reflect to the angle of incidence in the opposite direction. So we know the Snell's law, the angle of incidence equals to angle of reflection. So in the reflection, we know the what is the reflected angle, but in the scattering, it will scatter in the multiple random direction. So the type of scattering is a function of the wavelength of the incidence radiant energy and the size of the gas molecule, dust particle, or water vapor droplet. So basically there are three types of scattering. One is Rayleigh, second is Mie, and third is non-selective. So in the Rayleigh will occur with the gas molecules. Mie scattering will occur when it interacts with the smoke or dust, and non-selective will occur when it interacts with the water vapor. So we can see the size, relative size of the different gas molecules, smoke and dust, and water vapor. So these are the three sizes of different particles in the atmosphere. So in the Rayleigh scattering occurs when the diameter of the matter are many times smaller than the wavelength of the incident electromagnetic radiation. So Rayleigh scattering means when the gas molecules are very small as compared to the electromagnetic radiation, then the Rayleigh scattering will occur. So the amount of scattering is inversely related to the fourth power of the radiation wavelength. For example, blue light is scattered 60 times more than near infrared light. Okay, so because it is inversely proportional to the wavelength with the power of 4. So this is the relation between the wavelength and the scattered energy. So if the visible spectrum is small, then the scattering is high, otherwise it is low. So Rayleigh scattering is responsible for the blue sky because blue is scattered more using this relation. Then my scattering will occur when it is when the size of the particle is comparable with the wavelength of the electromagnetic spectrum, and the non-selective scattering occurs when it is greater than the incident electromagnetic radiation. So the scattering can severely reduce the information content of the remotely sensed data to the point that the imagery loses the contrast and it is difficult to differentiate the object from another. So these type of scattering will affect our remote sensing images. So we can see the impact of the atmosphere on the satellite images. So this is the impact of the haze in the satellite image, and this is the impact of the cloud in the satellite image. So these are the optical satellite images. Now what is the electromagnetic radiation? Now we have two theories. One is the wave theory and one is the particle theory. So according to the wave theory, the electromagnetic radiation travels in waves, the form of the electric and magnetic fields that make the electromagnetic waves. So this is the wave theory of the electromagnetic radiation. So this is the travel direction of the electromagnetic radiation. Then we have two components. One is the electric field component and another is the magnetic field component. So this is red is the electric field component and this one is the magnetic field components. So the speed of the electromagnetic radiation is given by the speed of light. 3 is equal to 10 to the power 8 millimeter per second. So this is called distance between the two crusts is given by the wavelength, and this is the frequency given by the number of cycles per second is given by the frequency. So the relation between the speed and light is c is equals to lambda nu. This is same like distance is equals to speed is equals to distance upon time. Now according to the particle theory, it suggests that the electromagnetic radiation is composed of the many discrete units called photons or quanta through the space. The energy of the quantum is given by the h into nu. So this is the theory according to the particle, means the energy contains in the particle is given by the h nu, where h is the Planck constant and nu is the frequency. So combining these theory, what we can get, like from the wave theory we have get c is equals to lambda nu, and from the particle theory we can get the energy is equals to s nu or energy is equals to sc by lambda. So we can see that energy is inversely proportional to the lambda. So the energy of the photon is inversely proportional to its wavelength, and the longer the wavelength of the electromagnetic radiation, the lower its frequency energy content. So as long as the wavelength of the electromagnetic radiation will increase, its energy will decrease. So what is the wavelength and what is the frequency? So wavelength is given by the speed of light by frequency. So the wavelength is the distance between two successive crusts of the waves. So this is the wave and these portions are called the crust and this is the trough. So distance between two successive crusts is called the wavelength and this quantity is called the amplitude. So this wavelength and frequency is also inversely proportional to each other. If higher the frequency, then lower will be the short wavelength, and when lower is the frequency, then longer will the wavelength. So here we can see the higher frequency, it is very much close to each other, then it is a shorter wavelength, and this is the lower frequency but having the higher wavelength. So this is the electromagnetic spectrum. It is consisting from gamma ray to the radio waves. So in our remote sensing, we mostly use the visible spectrum, infrared region, and the microwave region for doing our remote sensing. So here the wavelength will increase from gamma rays to the radio waves. So here is the shorter wavelength and here is the greater wavelength, and energy will decrease from gamma rays to the radio waves, and frequency will be decreases from here. So wavelength will increase, frequency will decrease, and energy is also decrease. So in the what are the atmospheric windows? Now gases absorb the electromagnetic energy in very specific region of the spectrum. These areas of the spectrum which are not influenced by the atmospheric absorption are useful for the remote sensor. Now we in the entire electromagnetic spectrum, certain portions of the electromagnetic spectrums are observed by the gases. So we cannot use that part of the spectrum for our remote sensing purposes. So available windows which are not affected by these absorptions are generally used for our remote sensing, and these windows are called the atmospheric windows. So the portion of the electromagnetic wave which we use for the remote sensing are called the atmospheric windows. So how the data acquisition occur? So basically the remote sensing instrument measures the energy received in three useful areas of the spectrum. So as I already told, like in our remote sensing, we basically use the three spectrum. First is the visible spectrum, we cover visible, near and mid infrared. Second is the thermal, and third is the microwave. So in the visible region, we have both passive and the active remote sensing. In the passive sensor, we use the solar energy reflected by the surface, and it will determine the surface reflectance. So in this remote sensing, we will use the visible part and infrared part of the electromagnetic energy, and basically we use the reflected part of the electromagnetic radiations. So it can be either passive or active. In the passive, we will use the reflected energy. In the active, we will use the own source of illumination like the LIDAR. It illuminates its own energy in the visible spectrum, and has been analyzed. So in the visible, we use the reflected energy. And in the thermal infrared, what we will use the emitted energy, means the energy which is absorbed by the Earth atmosphere, and after some time it will emit some energy. That energy we will measure. So that comes under thermal infrared remote sensing. And in the microwave remote sensing, they are work for the microwave region and for the higher wavelengths. So in which there are two possibilities, one is active and another is passive. In the active, we will use SAR for generating the images. It measures the amount of the backscattered energy, and basically scattering process it is inferring. And in the passive energy, it will observe the microwave radiation like the reflective portion. So in the same way, it will also do the passive remote sensing, but commonly we will see active remote sensing in the microwave if we will consider the imaging part. So this is the imaging part. This is also the imaging, and this is also the imaging. So in this lecture, we basically concentrate upon the imaging sensors, means about the satellite images. So we will use the passive remote sensing for creating the satellite images, and thermal and the microwave image, microwave region for creating the satellite imaging using the SAR. So basically, three electromagnetic regions are there. One is visible region, second is thermal region, fourth is the microwave region. So what is the visible region? The light which our eyes see. So our eyes are the remote sensor and can detect is a part of the visible spectrum. So what we will see in the it is in the visible spectrum. The visible spectrum wavelengths cover a range of 0.4 to 0.7 micrometer. The longest visible wavelength is red and the shortest is violet. Means in this visible range, longest is red and shortest is violet. So here it is the different component of the visible spectrum. So violet is from 0.4 and green is around 0.5 micrometer and red is 0.6 micrometer. So this is the visible range. In the infrared range, we have two parts. One is the reflected IR part and second is the thermal IR part. In the reflected IR part, we will observe the reflected energy of the infrared region. But in the thermal IR, we observe the emitted energy of the infrared region. So the radiation in the reflected IR region is used for remote sensing purposes, very similar to the visible portion. So like if we use the reflected IR, so it will same as visible IR remote sensing, but in the thermal region is quite different from the visible and reflected IR portion, as this energy is essentially the radiation that is emitted from the Earth's surface in the form of heat. So the thermal IR covers the range from 3 micrometer to 100 micrometer. So and this is the infrared region, which consists of two parts. One is reflected IR part and another is thermal IR part. And third is the microwave region, the portion of the spectrum of more recent interest to remote sensing is the microwave region from about 1 mm to 1 meter. So this covers the longest wavelength used for remote sensing. These longer wavelengths can penetrate through cloud, fog and haze, as the longer wavelengths are more susceptible to atmospheric scattering, which affects the optical wavelengths. So they can penetrate the clouds. So they are not susceptible to the atmospheric scattering. Okay, so and this microwave region is used for imaging the surfaces which are under cloud. So actually, so they are used for the remote sensing because they can penetrate cloud. So if we are using for the imaging sensor, so SAR is used for imaging the microwave region because they have longer wavelengths and they can penetrate through the clouds. So what are the remote sensing platforms? So basically there are three remote sensing platform. One is the ground and second is the airborne and third is the satellites. So what are the ground-based platforms? So it records the detailed information about the surface, which is compared with information collected from aircraft or satellite sensor. Means if we want to study any process, so first we will simulate that environment in the ground. So for that we will need some platforms. So to analyze any sensor properties, first we will do the experiment on the ground. So the basically that platform which we use for in the ground for analysis or simulation purpose are called the ground platform. These platform can be a ladder, crane or tall building. Okay. Second is the airborne platform. These are primarily the aircraft or the helicopters. These are often used to collect very detailed images and facilitate the collection of the data over virtually any portion of the Earth's surface at any time. They are generally used for aerial photography like photogrammetry techniques. These are also used for testing and any sensor before flying into the satellite sensors. So first we have to do some aerial survey type of thing, and we will study the sensor how it is doing in the airborne platform. Then before, if we will go for the satellite. So this is also an means of experimenting the sensor in the airborne before flowing into the space-based platform. Now there are also the airborne platforms which are called the UAV. So they are unmanned air vehicles. This is a new imaging platform for remote sensing application. They have the high spatial and temporal resolution, easy and quick to deploy for the data acquisition, variety of platforms and the sensors, relatively low cost to operate as compared to the aerial platform. So these are actually, these drones are recently been used for our remote sensing application, because we can fit any sensor in it, like thermal visible sensors we can fit it. It is relatively low in cost, and we can plan it. Means if we want to see any area, so we can do the any planning type of thing, mission planning we can sense. So all the things we can do with a single platform. Means with the UAV we can plan also, we can analyze also the data, and it is a relatively lower cost, and we can get also a high resolution images from the drone. Now, what are the space platform? In the space platform, we use the satellites for the remote sensing. So, satellites permit the repeated coverage of the Earth's surface on a continuing basis. Other than like the aerial and the drone, we have very limited coverage actually. But for the satellite, we have the global coverage. So we can do the remote sensing for the very much large area, and for entire globe we can see. So the path followed by the satellite is called orbit. So we will launch satellites in different orbits to see the Earth surfaces and any area of the Earth surface. So basically the orbit will follow the three laws. First is the Kepler's law. First law is the path followed by the each planet in an ellipse is the ellipse with sun at the foci. So this is the Earth, and this is the perigee, and this is the apogee. The second law is the line joining to the planet to sun shoots out equal areas in equal times. So this is the second law of the Kepler. And the third law, the square of the period of the planet is proportional to the cube of the semi-major axis. So these are the three laws which are used for the orbiting a satellite in around the Earth. So what are the orbital elements? There are 6 parameters for any orbit, which is called the inclination, right ascension of ascending node, argument perigee, eccentricity, major axis, and true anomaly. So these parameters are used for locating any satellite in a space. So what is the inclination? So in this figure we can see, if this is an orbit and this is the equatorial plane, means of the Earth, in the Earth plane. So what is the angle between this orbital plane with the equatorial plane is called the inclination angle. And what is the right ascension of ascending node? Means where it curves the Earth axis are 2 points. This is the descending point. This is called the ascending point. So how much angle which the x-axis makes with the line of nodes. So it is called the right ascension of ascending node. And what is the argument of perigee? This is the angle between the line of nodes with the major axis of the orbit. So if this is the orbit and this is the major axis, so what is the angle it is making with the line of nodes is called the argument of perigee. So first is the inclination. It is the angle between the equatorial plane with the orbit plane, and line of nodes what it makes with the x-axis, it is called the RAN. And what is the argument of perigee? What the angle makes with the perigee with the line of nodes. Now what is the eccentricity and same major axis? Same like the ellipse. What is the eccentricity and major axis? This gives the shape and size of the orbit. And the true anomaly is the angle between the major axis and the line joining the satellite and the center of the Earth. So this is the satellite orbit. then the near point is called the perigee, the farthest point is called the apogee, and the eccentricity is given by the a by 1 minus e square, and the position of the satellite is given by the true anomaly. So the angle between the major axis and the line joining the satellite of Earth on the anti-clockwise direction from the perigee. Okay, so this is the orbit, and if this is the satellite, what is the angle makes with respect to perigee is given by the true anomaly. So this angle is responsible for locating any satellite in the orbit. So basically there are three types of orbits: polar, equatorial, and inclined orbit. So if this is the Earth, then polar orbit is in the going from the north to the south pole. Equatorial orbit is around the equator, and inclined orbit is inclined at some equatorial plane is called the inclined orbit. So these orbits are responsible for different remote sensing applications. So basically the altitude of the satellite will give the image resolution, image swath on the altitude of the optical satellite. Means if we want for having the image resolution and image swath, so we have to see the altitude of the satellite. And if you want to see which latitude we have to see the Earth's surface, then we have to choose accordingly the inclination of the orbit. And how much the time to complete one orbit is called the time period. So basically we have three orbits: polar, equatorial, and inclined. Polar orbits is orbiting around North Pole to South Pole like this. Equatorial in the equatorial plane, and inclined, it is inclined with respect to some equatorial plane. Okay. So basically that polar orbits are used for our remote sensing satellite. They are called the low Earth orbits. So it the height ranges from the 700 to 800 kilometer, mostly sun-synchronous, near polar, and near circular. Okay, that satellite orbit is fixed in space and inclined at 98.7, and it will cross the equator at 10:30 a.m. local time, and it covers the 90 minutes per orbit. So these, like I have already said, like first is the polar orbit. The polar orbits basically used for our remote sensing. So it is not exactly 90 degree, but some of it is around 98.7. So these are the low Earth orbits. So our all the remote sensing satellite images uses these low Earth orbits, which is sun synchronous orbits. And for the communication purpose, we will use the geostationary orbit. So they are around 36,000 kilometer, and at the zero inclination, means it lies on the equatorial plane. So that is called the equatorial orbit. So this is the geostationary orbit, and this is the low Earth orbit, polar orbit. Okay. So actually it is used for the global coverage for the remote sensing. So in the communication, so it will the time period of the satellite is fixed with this rotation. So it is like it is fixed with this orbit. So it will see that area only, particular area only. So it moves as the Earth moves. So it is relative speed between this and this is 0. Now what is sun synchronous orbit? These are the near polar satellites for the inclination of orbit relatively to a line running between the north and the south poles. So they are near polar orbit around 98.98 degree inclination. So they are called the sun synchronous because it ensures the consistent illumination condition when acquiring the images in a specific season. So these satellites orbit are also synchronous because they cover each area of the world at a constant local time of the day called the local sun time. So if we want to see the images having the same illumination, so that type of possibility can occur only on the sun synchronous orbits, because if we use the sun synchronous orbits, then we can image any area with the same illumination. So if we use different date images, so we cannot see the effect of the sunlight. So and we can do the better change detection type of thing using the sun synchronous orbits, because they have the same illumination for different dates and seasons. So how to make a sun synchronous orbit? For that, the orbital plane is rotated as same rate as the Earth revolution around the sun. So we have seen like the orbit is rotating around the Earth with some inclination. So this orbital plane is also rotated as same rate as the Earth rotations around the sun. It is around 0.9 degree per day. So we can adjust the height and inclination such that the orbital plane also moves like the Earth moves. So it will create the same illumination with the different season also. So this here we can see the non-synchronous orbit. Here this is sun synchronous orbit. So here we can see if the orbit is like this, so we can have the same illumination for different season. But here we cannot see the same illumination at different seasons. So now what is the geostationary orbit? So this is the higher orbits around the 36,000 kilometer. So they are used for the communication purpose. So these geostationary satellites at altitudes of approximately 30,000 kilometer revolves at speed which match the rotation of the Earth, so that they seem stationary and relative to the Earth's surface. So this allows the satellite to observe and collect information continuously over the specific areas. So they means they will see that area only with the motion, because as the Earth moves, it will also move. So this will constantly see this area only. So it is used for our communication satellites. Okay. So weather and the communication satellite commonly have these type of orbits. So due to their high altitude, some geostationary weather satellites can monitor the weather and cloud patterns covering an entire hemisphere of the Earth. Okay. So now, what are the ascending and descending passes? So actually, for our polar satellites or our remote sensing satellites, and the satellites move from the south to north and then north to south. These are called the if it moves from the south to north, it is the ascending node, means south to north, it is the ascending node. And when it comes from north to south, this is called the descending node. So in the ascending node, the sunlight is not there, but in the descending node, the sunlight is there. So most of the optical remote sensing occurs on the descending node because the sunlight is present. So these are called the ascending and descending passes. So for the passive sensor, it heavily depends on the sun. So most of the remote sensing applications done for the optical images for the descending node. But for the active sensor, it doesn't requirement of sun is not there, so it can do the remote sensing in both the ascending and descending node. And also for the thermal imagery, they will do also in both ascending and descending, because it also don't need the sun conditions for the remote sensing purposes. So it also do day and night, so it will also do in the ascending and descending. So for the passive sensors or optical sensors, they will do most of the remote sensing in the descending node, but the active sensor and the thermal images can do the sensing in both ascending and descending node. Now what is the swath? Swath is the area image on surface by the satellite. So if this is a satellite, then it will image the surface in the across the track direction. Across track means if it moves in this direction, so it has two direction. One is along track in this direction with the movement of the satellite, and second is across track, which is perpendicular to the motion of the satellite. So this is called the across track. So this region is called the swath of the surface. So we have different swaths for different satellite. Like Cartosat 1 has 30 kilometer, Cartosat 2 has 9.6 kilometer, List 3 has 141 kilometer, and List 4 has 23.9 kilometer swaths. Now orbit is fixed in the space, so it will revolve like this one only. But with the motion of the Earth, we have multiple paths here, because here we can see the satellite is moving here, so it continuously moving in this direction only. But with the motion of the earth, it can change its imaging area. So in this way we can image the whole earth, because satellite is moving in this direction and earth is also moving in the west to east. So it is moving from north to south direction and it is west to east. So in this way we can image whole earth with the satellite images. So and this is the first path, this is the second path, this is the third path, and we can mosaic and we can have the image out of it. Okay, so these are the consecutive path which can possible with the motion of the earth and the motion of the satellite. So basically there are three type of remote sensing in the with respect to the wavelength. First is the optical remote sensing, second is the thermal remote sensing, and third is the microwave remote sensing. In the visible remote sensing we use the reflectance. In the thermal remote sensing we will use the thermal radiations or emitted energy, and the microwave region we will use the backscattered energy. So here only the passive sensor we are using. Here the passive sensor with the emitted energy, here both passive and the active sensor for the remote sensing purposes. So first we will talk about the optical infrared or OIR remote sensing. So they will basically use the visible spectrum. What is the visible spectrum? 0.4 to 20 micrometer means optical plus infrared. So here all the reflected energy is being sensed. So it is called the optical infrared. Means optical means visible portion, infrared means infrared portion. So our remote sensing will occur for the optical infrared portion, because all reflected energy is being analyzed in the optical sensing. So this is mirror, prism in these types of remote sensing. So what are the sensors used in the optical infrared remote sensing? One is the photographic and second the electro-optical sensor. The photographic system, images are transformed directly on a film. In the electro-optical sensor, the optical image is first converted into an electric signal and further processed to record and transmit the data. So this is the basically difference. Like in the photographic system we use the film, but in the electro-optical sensor the electromagnetic radiations like photons first they convert into the electric signal and then digitize to form a digital image. So mostly electro-optical sensors are used for the satellite sensors. So there are some basic terms in the optical infrared remote sensing. First, the instantaneous field of view or IFOV. So this is IFOV is the angular cone of the visibility of the sensor. So if it is a sensor, if we will see from here, so what is the angle made by the this means CCD? If we are using the charge coupled device, then this angle is called the IFOV, and it determines the area on the Earth's surface from the given altitude. Means it determines how much area it will see on the ground, and this is called the height of the platform. So this IFOV is the angle which is made by any CCD pixel on the image. Now what is the ground sampling distance? So if you can see, this is the CCD, means charge coupled device. Then if each pixel is of this length, then how much it is imaged on the ground. So how much GSD will be given by the CCD pixel side into the height of the satellite sensor and into the focal length. So if we will see the list 4 sensor, the CCD pixel size is around 7 micrometer and height is around 817 kilometer and focal length is around 982 millimeter. Then if we solve this equation, then we will get the ground sampling distance of 5.8 meter. So here simply what we are using, the means similar triangle we are using, means here this is called the focal length and this is the height and this is called the CCD length and this is called the GSD. So from these two triangles we are establishing a relationship. So this is given by this one, like GSD upon height, GSD upon this height is given by the CCD upon this focal length. So this formula comes from here only. So we can calculate the ground sampling distance from the CCD pixel size. CCD is the charge coupled device. So what are the multispectral scanning systems? Satellite remote sensor acquire the data using the scanning systems, which employ a sensor with a narrow field of view that shifts over the terrain to build up and produce a two-dimensional image of the surface. So this scanning can be of two types of. One is across track scanning, which is called the whisk broom, and second is the along track scanning, which is called the push broom scanning. So how this sensor will image the Earth surface? The two scanning mechanisms are there. One is the across track scanning and another is the along track scanning. In the across track scanning, we use the rotating mirror. And this will scan the terrain along the scan line that are right angles to the flight line. So here it is the across track scanning, means it will scan first pixel, then this pixel, then this pixel and this pixel. Like that it will scan this surface and it will form one line. And with the movement of this sensor, it will form the two-dimensional image. So it will scan pixel by pixel with the help of the rotating mirror. So and how the different components will be used, means if you want to have the multispectral image, we will use the prism for the different light, means the light will pass through the prism and different components of visible spectrum will made, means light, blue and green. And with the help of the dye grating, we will use the thermal component. Okay, so there are this is the we will call the across track scanning. So our most of the sensor like Landsat use the this across track scanning. It is also called the whisk broom. So in this scanning, we will the scanning will be done on pixel by pixel with the help of the rotating mirror. Okay, and another is the along track scanning. So this type of scanning is used by the modern sensors like the Cartosat spot sensor. So they will use the CCD. So what is CCD? Charge coupled device. So the Earth surface is scanned by a linear array of the CCD detectors. Imaging sensor consists of one line of active CCD elements and located in the sensor focal array plane. Means this is one line. So if we have 8,000 CCDs are there. So we have the 8,000 sample pixels in an image, and with the motion of the sensor, it will form a two-dimensional image. Means we have the 8,000 CCD pixels here. So it will illuminate the surface, and one single line will form. And with the motion of the sensor, it will form a line. So how it differs from the across track? In the across track, each pixel is we are moving the mirror, but here at one instant full line is made with the help of the CCD detector array. So so with the movement of the sensor, rows of the image is formed. So this is called the along track scanning, in which a single line is formed with the help of the CCD array. One array is there having 8K, 12K or 16K CCD pixels, and it forms the image on the surface. With at particular time, it will form one line, and with the movement of the sensor, it will form a two-dimensional image. So with the how the satellite form is like this one. Now, what is the advantages? So since each detector can measure the energy from each ground resolution set for a longer period of time, which improves the radiometric resolution. So because it has the more dwell time, means longer period of time, it see the pixel. So along track scanners have good radiometric resolution and also have the finer spatial and spectral resolution, because it observes the energy for longer duration of time. Because in the across track scanner, the pixels are moved, and it is we will do the scanning pixel wise. So energy to a particular pixel is less as compared to the along track scanners. So we are getting the higher dwell time and higher radiometric resolution, spatial and the spectral resolution. So these detectors are generally smaller. However, because each of the detectors have different energy falling, so there is somewhat non-uniformity in the sensors. So we have to correct some of this non-uniformity, means each of the detector will observe the light differently. So we have to find some calibration is needed for doing the uniformity among the every CCD pixels. So these are some of the radiometric quantities and units. Means what is the radiant energy, radiant flux, irradiance, existence, radiant intensity, and the radiance. So basically our sensor will measure the radiance of the sensor. So different units are there. Means what is radiant energy? It is the quantity of the energy carried. If we use per unit time, then it is a radiant flux. So radiant energy per unit time is the radiant flux. What is irradiance? If we are talking about per unit area, so radiant flux per unit area of the surface is given by the irradiance, and this is the reflected part. If we talk about the emitted part, it is called the excitance. So for the thermal remote sensing, we use this term excitance because it is the emitted energy per unit area. This is reflected energy per unit area, and this is the radiant flux emitted per unit area. If we talk about in terms of angle, means per unit solid angle in a specific direction, then we can get the radiant intensity and we can get the radiance. So radiance is dependent on the angle and the area of the illuminated surface. So different terms are there, but basically we are use the radiance and reflectance for our satellite images. So what is the solid angle? So this is a 3-dimension angle formed by the on the spherical surface. So it is a cone angle subtended by the portion of the spherical surface at the center of the sphere. It is equals to the area of the spherical surface divided by the square of the radius of the sphere. Its unit is radian and it is denoted by d omega. So likewise, normal angle is given by the angle is equals to arc upon radius, but the solid angle is given by the, we have to substitute arc with the area. So area by radius square. So that is the definition of the solid angle. So it is the area by the square of the radius. This is given by the solid angle. So how the satellite image will form? Now we know the CCD is capable of absorbing and sensing very nearly the incident photon energy. Means the light will fall on this CCD, and these CCD detectors convert the energy into the electric charge, because this CCD has the capability of sensing the photons. So they will convert the light energy into the electric energy, as we see have learned the photoelectric effect. So these photons are converted to the electrical energy. So the output of the CCD is continuous electric signal, which is generated by scanning the photo sensor in order by line and reading out their voltages. So first the energy is converted to the electric signal, and this electric voltage is then converted into the digital value through the quantization. Okay, so that analog to digital conversion will be there. So that analog value is converted to the digital value. So if this is a continuous signal here, so we have to do the quantization. So it is quantized to a different digital value here. So these recorded values are called the digital number. Means we have some energy, we have to digitize this. So we have a different digital number like 10 bit, 11 bit, and this digital image is downloaded in the receiving center, and again this DN is converted back to meaningful energy through the calibration. Okay, so first we can get the energy. These energy sensed by the CCD devices, it will convert to the electric energy to the voltage to the DN to the again energy with from the calibration. Okay, so we have to do some calibration to converge to the DN to the reflectance. So how the images look like? So digital image consists of the picture elements, which is called the pixel. So each image has a 2-dimension matrix. So each has some intensity. So we can see this is bright and dark pixels depend on the reflectance of the surfaces. So here we can see the values of the images. So an object reflecting more energy requires a higher number for itself on the digital image and vice versa. So it is a two-dimensional matrix of the digital numbers. Now, how to convert the digital number to reflectance? Because most of our satellite products, Indian satellite products and foreign satellite products, give the images in the form of the digital numbers. So we have to analyze in form of reflectance. So what we have to do, we have to convert that DN to reflectance. How we have to do? Because most of the satellite, along with the image, they will give the some meta file also. At that meta file, some calibration constants are also given. So like these two are the calibration constants are there. So they are used to convert using this equation, means these values are provided and this DN can be converted to the reflectance. And this is the not a sun angle correction. If you want to do the sun angle correction, then we can do the, again we can divide with the sine theta angle to do if there is a need of the sun angle correction. Okay, so basically some of the optical infrared sensors are the Cartosat 2, list 4, list 3 and Cartosat 2s. So different resolution are there. Cartosat 1 is 2.5, Cartosat 2 is 1 meter, list 4 is of 5.8 meter, list 3 of 23.5. So they have different like multispectral is there, means different wavelengths are there. These are called the multispectral sensor. If single black and white image is there, that are called the panchromatic sensor. So these pan means a black and white image. If different bands are there, then we call the color image. So we can have RGB images by putting different wavelength in R, G and B component. And Carto 2s satellites having the resolution meter of 0.6 meter for the pan and 1.6 for the multispectral sensors. Okay, and these are some of the sensors of the foreign data like Sentinel-2 and Landsat. So the Sentinel-2 we can get freely by registering the site, and Landsat also from the USGS side, freely data sets are there. And from the Indian sensor we can get from the data from the NRSC website which is located at Hyderabad. So now what is the panchromatic image? So it is works just like a black and white image. So instead of collecting the visible colors separately, it combines them into one channel and sensor can see more light at once. So higher reflectance are the bright pixel, lower reflectance are the dark pixel. It is higher spatial resolution compares to the multispectral images. So since we are seeing the visible spectrum into the one channel, means we can get a higher spatial resolution and all energy is combined into the one channel. So it is only the black and white images. So higher values will have the higher reflectance and lower values have the lower reflectance. So this are some of the images of the panchromatic sensor. Now what is the multispectral? In multispectral we will use the different bands and we will have the different band combination to visualize the color images. So basically the sensor will observe in the visible band, near infrared and shortwave infrared band. So these have different properties. Visible band is just like what we see our eyes. And what is NIR? In the NIR, healthy vegetation reflect more. So if you want to do some of the vegetation related studies, we use the NIR. And sphere band, rocks and soil that look similar in visible bands often have the strong contrast in the sphere band. So rocks and soil type of study we can do in the sphere band, because rocks and soil will look similar in the visible band but have a strong contrast in the sphere band. So they are particularly useful for telling the wet earth from the dry earth. So these if we have the multispectral sensor, because the multispectral sensors have different bands depend on the different wavelengths. So we can combine the different bands and we will see the effects of any natural surface depends on its wavelength properties. Okay, so like healthy vegetation is looking more in the NIR, so we can use the NIR band for the vegetation study, and for the soil study we can use the sphere band. But if you want to see just like that what the image is, that we can use the visible band. So now what is the spectral reflectance? So different terminology I have explained, like radiance, radiant flux, intensity is there. So what is the spectral reflectance? Spectral reflectance is the energy or wavelength reflected from the object upon energy of wavelength incident on the object. So this is called the spectral reflectance into 100. So basically what we want to get from the image, it is the spectral reflectance, because ordinarily the images are given by the DN numbers, and these DN numbers can be converted to the radiance or spectral reflection with the help of the calibration constants. So ultimately we will study the spectral reflectance in an image. So what is spectral reflectance curve? It is a graphical representation of the spectral response over a different wavelength in the electromagnetic spectrum. Okay, so how it will look like if we have different wavelengths. Okay, this is the different wavelength, and it is the reflectance. So spectral reflectance curve is a curve between the reflectance and with the wavelength. So if we have three features like dry soil, green vegetation, and clear water body, so this is the response of the vegetation, green vegetation. So at different wavelength we can see how the vegetation will appear at different bands. So this is the spectral response of a vegetation at different wavelength, and this is the spectral response of the water at different wavelengths, and this is the spectral reflectance of a dry soil. So we can see the how the natural surfaces behaves in different wavelengths. So if we have the multispectral imagery, like we have different energy in different bands, so then we can see their properties in different bands, and we can classify the different and natural features. Like here we can, if we can see that like NIR. So in NIR, here in the spectral curve we can see this is the this is the NIR 0.8 micrometer. So here we can see the water has the lower reflectance, and dry soil is greater than water, and vegetation has the highest reflectance. Okay, so this energy is given by the spectral curve, and the image itself, it is showing like this is the water, so it is appear as a black, vegetation appear as a bright, and soil, this is a soil, it appears as a gray. So this is black, this is a gray, and this is a bright pixels. So NIR, the different features looks accordingly to the spectral curve. Likewise, in the sphere band, we have the this is the sphere band in the infrared region. So here we can see like the reflected water has the lower value only, but we have the soil has the higher value and NIR has the lower value. So same sphere band, water is appeared as a black, but this soil is appearing as a white, and the vegetation appear as a lower value. So we can see like same feature has different reflectance values at different bands. So this is the natural color image. So here is this is a NIR, this is a sphere, and this is a natural color. So we can see like this is the blue color, and here you can see that this is soil. So soil has NIR, it has lower value, in a sphere it is a higher value, and vegetations we can see a higher values in the NIR bands and lower values in the sphere band. So we have different band combinations and to visualize our image. So if we use the natural color composite, we will have the RGB in red, green, and color blue, and false composite if we use like different colors like NIR, green, and blue, and to have a different band combinations. So in the natural color composite, we will use the red band in the red, green band in the green, and blue band in the blue. Okay. And in the FCC, we can use red band in the NIR, green band in the red, and blue band in the green. Why we will use FCC? Because we want to study the vegetation. As we know that vegetation is very much visible or very much has the property in the NIR band. So we are giving the red band as an NIR band, green band, red band, and blue band as a green band. So we have the false color composite. So how the image looks in NCC and FCC. In the NCC, as the feature we will look our eyes, it appears in NCC, but in the FCC, the images look like in different way. Means here the vegetation appear as a red, and water appear as a blue. So these are some changes we can make within the band, and we can visualize the certain things according to their spectral properties. So what are the resolutions? So basically there are the 4 resolution: spatial, temporal, spectral, and radiometric. So what is resolution? The ability of the sense system to render the information at the smallest discretely separable quantity in terms of distance, wavelength, time, and radiation. Okay, so means if we want to discriminate the two objects with respect to spatial distance, with respect to wavelength, or with respect to time, or with respect to radiation. So we have the 4 resolution. So first we will see the spatial resolution. This is the resolution, this is the ability of the sensor to detect and distinguish small object and fine detail in the larger objects. Means this we can see this is a 10-meter resolution, this is 30 meter, and this is the 80-meter resolution. So we can see the fine details in the higher resolution images. Okay, so this is 10-meter resolution, means the object which are separated by the 10-meter we can visualize in this image. Here the object which are separated by 30-meter we can visualize in this image, and the objects which are separated by the 80-meter resolution we can visualize in this image. So we cannot visualize the 10-meter objects in the 80-meter resolution images. So this is the concept of the spatial resolution. Now what is the temporal resolution? Means it represents the frequency with which a satellite can revisit an area of interest and acquire a new image, and it depends on the field of vision and the satellite's orbit. Like how frequently it will see the area with the next orbit. So Sentinel-2A has a revisit of the 10 days, means it can see the same area after 10 days. So these are the 2 images of the Sentinel, which acquired on 2nd April 2020 and 12th April 2020. So you can see the changes within an image. So if it revisit time of the satellite is good, then we can have a high temporal resolution. If the revisit time of the satellite is low, then we have the coarse temporal resolution. Means how frequently the satellite will see the image is the temporal resolution. So spatially means how the satellite will see 2 different objects spatially, and temporal resolution is to see the feature temporally, means how frequently it will see the feature. Third is the spectral resolution. It means how the image containing the spectral information, means it determines how many number of bands in the satellite in the image. So if we will see the multispectral images like Landsat, it has the 8 number of bands. It means we have the different wavelength at 8 bands. Hyperspectral images have the, like Hyperion has the 220 bands. So we can see this is any feature we can better discriminate spectrally in hyperspectral as compared to the Landsat, because if we draw a spectral curve, so we have the information of every band, every wavelength in the electromagnetic spectrum, but here we have the less information. So we can see like hyperspectral sensors have the high spectral resolution, and the multispectral sensor have the low spectral resolution, and panchromatic sensor has also have a very low spectral resolution. It depends, means how at different wavelength the sensor is seeing the Earth's surface. Third is the radiometric resolution. Now I have told while we are having the energy in the images, we have to convert, we have to quantize the continuous to the discrete. So that energy we have to make a digital. So how we are doing the digital conversion means any number is there. So at how many bits we are quantizing the image. So we can mostly the satellite list 3, list 4 at 10 bit, Landsat 8 has 12 bit. So if we have some continuous energy signal, so if we can say like 10 bit means 2 to the power 10 values it can have, like 2 bit it have 0, 1 values, 3 bit 2 to the power 3 8 values, or 8 bit like 255 values. So that way that is called the radiometric resolution, means what is the bit value of that image. It is 10 bit, 12 bit, 8 bit. So if higher will be the bits in the image, it has the higher radiometric resolution. Like this image, it is, and these are the 4 different bits images. So this is a 12 bit image, 6 bit image, 4 bit image, and 2 bit image. So how you can see like entire energy is divided into only 0 and 1 value. So it is a 2 bit image. Here 2 to the power 4 values. So you can see some of the segmentations are there. It is not looking good. So if energy, if the bits in the image is good, then we have the radiometric difference easily identified in the higher bit images. So and this part I have told about the reflected part. Now I will tell something about the thermal part. Now as we know, this is the how the target interacts with the electromagnetic radiation. So we have the incident, reflected, and transmitted. So some of the energy is also absorbed by the surface. Then after some time, this observed energy is emitted by the natural surface, and this emitted energy is sensed by the thermal sensors. So in the thermal remote sensing, what we will use, we will see the emitted radiation, how we will sense. So it will occur in 3 parts: near infrared, mid infrared, and thermal infrared. So this near and mid is used in the OIR part, and the thermal part we will use in the thermal remote sensing part. So there are different atmospheric windows in the thermal infrared remote sensing, which is from 3 micrometer to 5 micrometer and 8 micrometer to the 14 micrometer. So these are the atmospheric windows which are available in the thermal remote sensing, which we will use for the remote sensing. So because thermal the components of the earth thermal radiation is large, hence the TR region can provide the useful information directly or indirectly with the various phenomena. But mid infrared have the same energy in the reflected solar radiation in the daytime. So we will use the thermal infrared in the day and night time, because it has different component of the earth thermal radiations. So what is the black body? Black body means if it is absorbed, then it will absorb all the energy and it will emit all the energy. So it will follow 3 laws: Planck's law, Stephen Boltzmann law, and wind displacement law. Means a black body will absorb all the energy and it will re-emit all energy. So it will follow 3 laws. One is the Planck's law. So this is the Planck's law. It is the energy is given by this one. It depends on the wavelength. Second is the Stephen Boltzmann law, in which the energy is given by the integration of the Stephen Planck's law. So it is given by the total energy, how it is there. It is the sigma into T to the power 4. Means the higher of the temperature of the radiator, the greater the amount of the radiation it emits. Means higher is the temperature, then the greater amount of radiation it emits. And similarly, if we differentiate the Planck's law, we can get a wind displacement law. Here it is means maximum wavelength is given by A by T. Hello. Okay, ma'am. Okay, ma'am. Faster. So I will tell about what are the different characteristics of the thermal image. So this is the thermal image. So how the different images, some different features will exhibit in the thermal remote sensing. So during the day, water appears. So in this diagram, what we will say, this is if we will see, this is the midnight, noon and midnight. So rock and soil has the larger variation, and vegetation has the lower in the day, and damp terrain has lower, and metallic objects has the lower. So we can see at the night time, water has the higher thermal radiation as compared to the rocks and metallic objects, but in the daytime it has the higher portions. So this is the thermal image at the daytime, night time. So we can see the water appear as a higher temperature, and this is the land which is appear as a black. Here it is a black, and this is the higher value, and this is the NCC image in the day. Okay. So this is the thermal images how we perceive. Now we will see some of the microwave remote sensing. In the microwave remote sensing, what we will do, we will use the antenna for focusing. It is used for the larger wavelength. Okay. So basically we will use the SAR for the microwave remote sensing. So it has the all weather observation system. It will sensitive to dielectric, and it has the penetration capabilities, and sensitive to topography and polarimetric, and sensitive to metallic and artificial objects. So it has the day-night capability. It is insensitive to cloud covers. 10 times more images are available, multi-incidence and multi-resolution. So how the raw image of the SAR will look like? So this is the raw data, and this is the process data of the SAR. So basically we use the synthetic aperture radar, which use the higher resolution images by the moving of the radar. With the motion of the radar, we create the high resolution images in the SAR. So basically, and these are the parameters which we have in the SAR image, like wavelength, polarization, and incident angle, and target parameters like surface roughness, dielectric constants, moisture, and geometrical shape. So different wavelength we can use, like X, C, S, and L band. So when the wavelength will increase, the penetration capabilities will increase. So we have different satellite like Terra X, Reset 1, Nova SAR, CSAT, and Airborne SAR. So we will see how the SAR image look like. So this is a SAR image. Here the bright portions are given by building, and water appear as a black, and vegetation appear as a moderate. And this is the how SAR and optical images look like. So bright returns will given by the metallic objects. So in optical image we cannot see this bridge here. So these are the comparisons between the SAR and optical. So it is a complementary source of information. So that is all from my side. Thank you. Any questions are there?
Thank you so much, sir, for sharing all the nuances of the various principles and algorithms related to remote sensing in a quite informative way. So moving ahead with question and answer session, if you have any query, you can directly interact with Ashish, sir. Do we have any query? Mr. Sayed, do you want to ask something?
Yes, sir.
I'm repeating it again. If you have any question regarding the presentation, you can directly interact with Ashish, sir.
सर 11 बजे वो रमेश पोखरियाल सर का इनॉग्रल सेरेमनी है, तो वो अभी 11 बजे से स्टार्ट होगा, उसमें ज्वाइन होना है। बाकी आपका सर मैं यहाँ पे हूँ।
Yes, sir. I was wondering regarding whether the data, that remote sensing data is available
हाँ सर, वॉइस क्वालिटी अच्छी है सर,
so that we can access the data.
I'm not able to hear you. Your voice is not clear.
हाँ अभी ठीक दिख रहा है.
Sir, whether the remote sensing data is available for free
sir,
through
आपकी
any government portal, like in the Bhuvan, I used to get some relevant data,
मैं
but
आपको एक बार स्क्रीन भी दिखा देता
is
हूँ.
MIR data available
तो आप
through Bhuvan portal and all?
हालांकि अभी आप शेयर करेंगे जो नया वाला है, मैं पुराना वाला.
You are talking about the free data of the satellite images? I'm not able to.
Yes,
the
sir,
free
yes,
data,
sir.
yeah, you can from the NRSC Indian Remote Sensing Satellite, you can get the data. You have to register there. The Bhuvan portal is there. It is for the Indian sensor satellite. For the foreign satellite, Sentinel and Landsat data is there. So for the Sentinel, we have the SAR and optical. Both are free data sets, and you can register and you can download. And Landsat, all the optical imagery are there to download the data. Just you have to register and you can get the data sets.
Okay, sir. Thank you.
अच्छा पूरा स्क्रीन आपको मतलब ये ठीक है सर?
इसको जरा फुल स्क्रीन करिए.
ओके.
Anupal Jyoti, do you have any question?
Yes, ma'am.
Kumar.
Yes, sir. I'm Anupal Jyoti Datta. I'm a researcher at IIT Kharagpur. I want to know, like, whether this temperature data is available for the subsurface rocks or minerals like granite and all.
Actually, the thermal Landsat data is there. Na Landsat, they are observing the thermal infrared region. So that data you can see for the different features like that one, how it is there. So it is of course resolution, but still you can observe the things from the thermal images of the Landsat.
Thank you, sir.
Yes, sir.
Thank you so much, sir. I think we are running out of the time. So thank you again, sir, for finding time and sharing your experience with us.
Okay.
This is all with the question and answer session. Thank you.
Thank you, sir. Thank you, Ashish, sir. It was very effective and clear presentation. Thank you, sir.
Okay. Thank you.
Okay, a little information for everyone. As I have mentioned earlier, all of us have to join the common inaugural ceremony organized by AICTE. A link related to the same has been already shared through the mail and even in the WhatsApp group. We will gather again sharply on 12:40 p.m. for the second session of the day. So now we will join the common inaugural ceremony organized by the AICTE. So till then, have a nice day and thank you everyone.
स्क्रॉल करने के आप बताएंगे ना, जैसे जीसी रायपुर का आप बोल रहे हैं तो एक्सपेंडिचर का है तो
Thank you,
एक्सपेंडिचर
Ashish sir.
जूम करके दिखा देता हूँ एक्सपेंडिचर फिर आप जैसे ही उनका गेट का बताएंगे तो गेट में
So all the participants are requested to join the YouTube for combined inaugural function, and at 12:40 we are meeting again for the second technical session.
अच्छा ठीक है सर, मैं एक बार कोशिश करूंगा सर और
3 बजे अपन लोग बैठ जाते हैं 5 मिनट के लिए.
हाँ बिल्कुल सर.
लेटेस्ट वाला भी अभी तुमको भेज देते हैं, वो जो शीट है ये वाली.
हाँ ठीक है सर.
उसको शेयर करके देख लेंगे फाइनल.
हाँ यस सर.
तो वैसा ही करते हैं, तुम सब ज्वाइन कर लो वहाँ पे.
यस सर मैं ज्वाइन कर लेता हूँ वहाँ पे.
थैंक यू.
ओके सर. हाँ यस सर.
ये क्या है ना, थोड़ा सा यहाँ पे ना नेटवर्क फ्लक्चुएटिंग है.
अच्छा.
और बार हो जा रहा है, डिस्कनेक्ट हो जा रहा है.
हाँ
तो अभी ना दूसरा नेटवर्क इसमें यूज किया. ये वाले में थोड़ा सा सिक्योर लग रहा है.
अच्छा यस सर.